charge it while we're in the break. So, okay, cool. So the next thing we're going to talk about is two different things. We're going to talk about binary numbers and hexadecimal numbers. And I essentially think of these as the language computers speak in. So this is essentially computer language. And I want you to know a little bit, just a little bit about this, because I don't know if you have taken any programming classes. Anybody done any programming in here? No. Yeah, that's what I thought. Maybe, perhaps that was the case. So a computer at its essence is just a bunch of switches underneath. And I really mean this in the most literal sense. A computer at its finest details are a bunch of off and on switches. When I was young, James has got me hooked up over here. When I was young, I'm not young anymore. I want to show you something here. Sorry, the whole beginning of this class just completely.
Sorry, that was probably my fault.
It's okay, it was fun. You know.
Yeah, it was pretty fun.
I had fun hanging with y'all, so that's good.
I want to take a class on that. Like, I'm serious.
On what?
I want to know where like these theories and everything come from. I don't believe people are this intelligent. I feel like it's just drugs.
A lot of things did come from drugs, but I don't know how much math did.
So a lot of math came. A lot of math came from vodka. Like there was a lot of Russian and Polish mathematicians who were just complete alcoholics and would stay up late into the night drinking.
And they always are. And we glamorize these like mathematicians, these philosophers to be like these really intellectual people. Let's be real. Like they probably all have their own issues, you know?
Everybody's got their own issues,
yeah.
For sure. So when I was like 12, we couldn't afford a computer. I really wanted one. I wanted an Apple II computer. I was gonna like build a computer friend because I was a nerd, so I needed to like make friends out of nothing, you know? And hopefully this computer would be my best friend in the world, and I would make it do all sorts of things. Well, we couldn't afford one, so I would go down to the computer store where they had a bunch of Apple IIs set up, and they would let us use them. So we would go there and we would buy books of basic programs and enter the programs and then play the games and spend hours there just doing this stuff. And then I saw this book one day. Let me show you this book. I saw how to build a working digital computer, and I thought, all right, I am gonna build my computer. I don't need to buy an Apple II. And look, it's made out of paper clips. So I was like, yes, this is my answer. So that computer right there, you can build it. Let me show you. Someone actually did. I ended up giving up on this thing. But I want to show you what this computer actually looks like. Oh, here we go. Here's some maniac who built this computer.
You want to be an IT pro. So
You want to be an IT pro? Yeah.
No.
No. Okay, there it is. He built it.
Computer that was built over the period of about 9 months. I built it to scale from this book from the 60s, How to Build a Working Digital Computer. It is an actual electrical and mechanical computer capable of adding, subtracting, multiplying, and dividing, and making a few logical decisions also. These are the components. First of all, the decimal to binary converter, core storage, program drum that holds the paper program that you see there with holes punched in it and is read by the various read heads, which then connect to the control unit. Control unit directs a human operator in what to do next over on the arithmetic logic unit, which actually adds, subtracts, multiplies, and divides. in octal, and the binary result is output in a series of lights.
That's
near
your
the top
output right
here,
there, those 4
and then
lights.
transmitted over to the last stage of the computer, which is the binary to decimal decoder unit, and the output comes out here on these lights.
Oh, that's if I want to.
So this is my project. It was a lot of work. If anyone's interested, I'd be happy to
So this is my
give a
project.
demonstration.
It was a lot
in
of
my
work.
next video.
I think he said
Please
7
leave me
months.
comments and let me know if you'd
9.
like.
9 months, is that what he said?
Thanks very much.
So this thing is crazy. It's not like any computer you've ever seen. It's a computer where you say, I want to add a couple of numbers. Let's get this shit off the road here. There we go, shut down, thank you. So you want to add 7 and 8 together. Where's me pens? There's me pens. And so the first thing you would have to do is convert. So you want to add 7 plus 8. You had to encode these first into binary. And I'm going to show you how to do this today. This is the language of switches, offs and ons. And it's what every computer works with, including that weird plywood monstrosity. And then they would just tell you, okay, now you've entered those, go flip switch A. And then you'd have to literally run down to this box, flip that switch, and then a new light would come on and say, go flip this other switch. And you'd run around, so you'd be running around. It would take you like 15 minutes to add those 2 things together on the computer. It was not the computer I envisioned. I wasn't going to be playing games on this computer. But it did teach me a lot about what goes on underneath. Let me show you how a computer actually adds some things to give this a little bit of context. So our main digits for a computer are from binary, the binary number system, and this is base 2. We really only have 2 numbers. We have 2 digits. 0 and 1. And that's it. 0 is off, 1 is on, just like a switch, off and on. And this is all a computer knows. Everything else is just fancy surface interfaces. Everything else is going on under the surface at that level. So here's how a computer actually adds 2 numbers together. You've got an input A, you've got an input B, and these are either 0 or 1. And you could think of this back to the very start of our class as false and true. Remember how we did basic logic at the beginning of the class? So false and true are things that a computer can understand as well. So you've got 2 numbers you want to add, and then you've got maybe a carry from a previous computation. So this is carry in. And I'm going to draw this picture for you because it'll probably be the last chance you have to see such a thing if you're not going to become an electrical engineer. But it relates to stuff we've done. So I'm going to write XOR in there, that's XOR. And then this comes down like this, and these 2. So wherever there's a dot, those are wires that are connected. If there's no dot, they pass over each other. And then we've got C in, and that keeps going. And then this comes down, and this comes down. We've got this, and then here, this says and. And then, just give me a second to get this all put up. This one comes out this way. This has got an output. And then these 2 go into another thing like this, XOR, that's out. This is your sum, it comes out here. And then these 2, let's see, okay, carry from here, this comes down, this is an and. And these are the logical operations. We didn't talk about XOR, but you'll understand it easily. You get it, and then these 2 come like this. And then this is an OR gate. And this is your carry out. So this is called a full adder. And I just think it's cool to know what is going on deep down in these things that have become basically extensions of ourselves. right? So a full adder. So the way this would work is I pass in either a 1 or a 0, a true or a false. And let's say here I passed in a 1 and a 1, and there was no carry from the previous computation. Now I know this might seem a little hazy, but just stick with me a bit. So this means just apply a current here, send in some voltage, don't send any voltage here. And so these things come in and travel. So check it out, this is true. You can think of this as true, true, and false if you want. Two trues come in. This is called exclusive OR. And it just means that, here, let me show you the truth table. So we've got A, B, and then A exclusive OR B. And you understand this because we talked all about this. So if they're both false, then the output is false. If one is true, the output is true. And if both are true, the output is false. So this means it's only true when they're opposite values coming in. Otherwise it returns false. So you pass two trues in, pass these ones in. They go to this gate. So now check it out, there's a T and a T coming in here. So it outputs an F. So right now there's no current coming out that way. And then we come down here and we've got a true coming in and a true coming in. And this is the AND. So we have true and true. Just like you know, that's true. That's one of the properties of that AND operation. So I got a true coming out here. And let's see, what do we got coming through here? False is right in here, false is right in here. And so now I get over here, I've got exclusive OR on a false and a false coming in. So the sum that comes out is false, aka a 0. And then what do we got here? We got a false coming in and a false coming in. So F and F, false and false, is false. Back from those days, so there's an F there. And here's an OR gate. And this means true or false, which comes out as true. When one of these two is true, then you get a true out. So we get a true out of here. So what this is saying is that if a computer wants to add 1 and 1, essentially, the output is a 0 with a carried 1. Now this right now doesn't make any sense, but I'm gonna make this make sense in the next like 10 minutes or so. Underneath your computer, you've got millions of these inside each little chip, just doing this basic operation. So everything a computer does comes down to the first 3 weeks of our class. Really. Let's talk about what I mean with this binary stuff. So let's talk about binary, base 2. Before we do that, it's probably better to just refresh our memory on how our own number system works. So recall, base 10. So if I write a number like this, 335.24, you would just take that number and go, oh, that's 335.24. Maybe it's dollars or something like that. We don't know. But what does this really mean? This means that I've got these slots filled. So I've got a point here, that's my decimal point. And then here I've got ones. Here I've got tens, here's hundreds, and then thousands come out this way, and so forth. And then to the right is tenths, hundreds, thousands, and so on. So this is what we live in all the time. This is all the work we're doing. These are the decimal places. So when I write this number, what it means is I've got 3 hundreds, 3 tens, 5 ones, 2 tenths, and 4 100ths. And so I interpret that number just naturally because we're taught to understand those numbers. But at its deepest level, this is what that number means. It's a collection of quantities. And each place tells you how many of that quantity are in there. So let me write this out a little bit differently here, because this is going to be probably some stuff that feels a little awkward for a few of us. But this is 10 to the 0th power. If you take a number to the 0th power, it's always 1. It's just defined to be that way. This is 10 to the 1st. This is 10 squared. Notice how the exponent equals the numbers of zeros after the 1. This is 10 cubed, and then that keeps on going. 10 to the 4th, 10 to the 5th. What's this one? What power is that of 10?
-1.
Beautiful, thank you. It's 10 to the negative 1st. So negative exponent just means 1 over that. This is, what's that guy?
-2.
-2. Solid, Paul. So that's just 1 over 10 squared, 100. This is 1 over 10 to the 1st, 1/10. And then 10 to the negative 3rd, and so on. We only use base 10 because we have 10 fingers. We could use base 20, like the Mayans, because we've got 20 digits all in total, right? The Mayans used base 20. So in the Mayan system, remember how that worked? We had the 1s, we had 20s, we had the 20 squareds, aka the 400s place. And so this is just 20 to the 0, 20 to the 1st, 20 squared. And the Mayans were just doing the same thing, but with a different base. And they had 20 different numbers to put in each of these. We've only got 10. So let's go now and extend this to other places. And let's go to the computer's language, base 2. I got 2 digits. Oh, shit. Ah, well, fuck it. Later. Once again, my video is not suitable for children. So, all right, so let's talk about base 2. Again, binary. So you've got places here, like so. We're gonna have a little point. It's not called the decimal point. Now it's called the binary point. And what I'm about to show you, I gotta tell you, very few people know what you're about to learn. Very few people. Even like I've got 400 level math students, they don't know any of this. This first place, think about how we had this. This was 20 to the 0 base 20. This was 10 to the 0 here. And it's the same thing here. It's just 2 to the 0. The 1's place. And then since my base is 2, these places are going to be in that same rhythm. Just higher and higher powers of that base. So there's 2 to the 5th. What's to the right here? So let's look at the rhythm. What's the rhythm? Base 10, here's the first one to the right. Base, we don't have base 20 thing. They didn't do decimals. What do you think is here? What's the rhythm on the exponents? They're going down, right? So what's the next place down?
-1.
-1, beautiful. Yeah. So that's the halves place. And then what's next, Braden?
-2.
Beautiful, sir. Thank you. And so that's 1 over 2 squared. That's the 4ths. And then 2 to the negative 3rd, right? We just follow with that rhythm. That's the 8ths. So that's 1 over 2 to the 3rd, 1/8, and on down. And of course, this keeps on up this way. So if I write a number and I tell you, hey, this following number is in base 2, and I write 1011.01. And I tell you, and we can use this little notation, say that's base 2, just so you don't think that's 1011. It's not, it's base 2. The way to interpret this and convert this to decimal, so this is binary. If I want to convert it to decimal, I just lay this into this tray and see which of these places up here are kicking in. So this is the 1's place. This is the 2's place. This is the 0's, excuse me, the 4's place, and this is the 8's. Look up there, so that's 2 cubed, 2 squared, 2 to the 1st, 2 to the 0. This is the halves place. There's none of those. But let's write it out here. That's how many halves I have, and then here's how many quarters I have. So to convert this number, there is 1/8, no 4's, 1/2, 1/1, 0 halves, and a quarter. And then I simplify that, and that's 11.25 in base 10. Take a look at that and make sure you understand that computation, because you're going to have to do that. We're just learning a new number language. Let's see if we got this. Can you please convert the following number? And you might have to go out, you might have to extend out a little bit, but can you please convert that to base 10? Definitely some writing is going to be handy. You got those places identified, right? And notice how there's a nice rhythm here on these places. You just multiply by 2 to get to the next one to the left. So I had to go all the way up to 32 here. So I've got something in the 32 slot, so I've got a 32. None of this stuff. I do have a 2. And then over here I've got a quarter, a half plus a quarter. So the final answer is 34 3/4, or 34.75 in base 10. Let me know if that needs some clarification or explanation at all. And so this is basically how you're going to do problem 5 on that sheet that I handed out. Paul, yes sir.
So you take 32, and why do you add just the 2 and the half?
Okay, so these, the ones or the zeros tell me if this number is included, essentially. Okay. So I've got a 1 in the 32 slot, so I definitely have one of those.
I guess.
Say that again?
That's like true.
Yeah, you can think of it like that, yeah, true. Do I have a 32 in this? Yes. 16, 8, 2, no, none of those. But I do have a 2,
okay,
and then no 1s. Does that?
Yeah, that makes sense.
Okay, awesome, cool. I like that thinking of it as true and false. Is it in there or not? That's great. Yeah. Any other questions on that?
It's not a question on this, but I just remembered that I have an advisory meeting at 3.
Okay, that's
So I
okay.
gotta
I'll
keep
do
up.
recording up. Fair enough.
At 3. I know, but I don't want to.
Well, don't show up late for the advisory.
No, she'll get mad at me.
Send her to me. Tell her you had something important going on. You shouldn't be making appointments during class anyway, right?
I didn't make an appointment now. She made it because I have to see her before I register.
Oh.
Because I have like 2 minors and 2 majors.
Can you be late for your appointment a little bit? We could be doing stuff now
Okay,
instead
okay.
of having this
Sorry,
conversation.
sorry.
Let's get some shit done. That's okay. But if you gotta go, you gotta go. Okay, so that's how you do problem 5. You're gonna have to do that, and then there might actually be another one on here. Nope, that's the only one we can do now. How do we convert to base 2 from base 10? So this is, I want to teach you a nice little algorithm. Again, very few people know this. But this is how you convert to any base from base 10. So, how to convert from base 10 to binary, and then I'll show you how to do it for any or any other base. which is going to knock out a bunch of problems on that sheet too. Let me show you how this system works with something we understand. Let's just think, let's convert a base 10 number to base 10 using my little plan here. It's not my plan, this is an ancient plan. But just notice this, don't write this down. I want you to just follow this. Let's say I was going to convert 345 to base 10. It's already in base 10, but here's how this works. I divide by the base, so I'm going to divide by 10. How many times does 10 go into this number? Whole times. It's the full number of times you could divide 345 by 10.
34.
34, yeah. So if I divide that by 10, it's 34 times, that gets me 340. What's my remainder? 5. So make remainder over here, 5. Yeah. So over here, the key thing in this whole process is recording these remainders as we go down. So divide by 10 again. How many times does 10 go into 34? 3. What's the remainder?
4.
4, indeed. So the remainder is 4.
Sorry.
That's all good. And now 3 and 10 doesn't go into 3.
No.
So I'm done. But look at what the remainders spell out. The number. 345.
Oh.
Okay? That's the secret. That's how you convert to any base. So if I want to convert to base 2 instead of dividing by 10, I divide by 2 and keep track of the remainders. So for example, let's actually do this one. Let's do 34. This is for the whole parts here. So let's convert 34 to base 2.
Okay.
So divide by 2. How many times? How many times 2 go into 34?
17.
17. Is there a remainder?
Nope.
Nope. So remainder 0. How many times does 2 go into 17? 8. Remainder? How many times 2 go into 8? 4. Exactly. Remainder? 0. Zip. How many times 2 go into that? 2. Remainder? Last time, 2 can still be divided into that, and we get, I know you know that one, 1. And the remainder? 0. Spell it backwards. 1, 0, 0, 0, 1, 0. Look at the pattern of that number up there. So you read these backwards. 1, 0, 0, 0, 1, 0. That's it. That's the base 2 conversion. And it agrees. We know that. We checked ourselves on that. And that's it. Let me give you one to do. I think we'll be working on this stuff for a couple days more. We'll definitely need to talk more on Monday because we're going to talk about base 16 too, and that's where the word feed. So Christina looked on the sheet. She's like, "Is there a misprint on here? There's words. How do I convert feed? Feed is a number. Feed's going to be a number you'll understand, but it's probably not going to be till Monday. So hold on to this thing. All right. So please convert." 137 base 10 to binary. So it's the continue to divide by 2 and record those remainders. I'm logging you out here, James. Thank you for your computer account. You don't have to write divide by 2. You know that's what you're doing, so I just put that there for us to have something to look at and to kind of help guide. it 68 for the first one? Is that 2 times, is that how many times 2 goes into there? That seems right. Yeah. And you could always just get your calculator out and you could go 137 divided by 2 and it'll give you like 68 point something. You just grab that whole part. So if you're having trouble figuring something out, just use your calculator to get that whole part. And the remainders are what we keep track of. And as soon as you get to 1, you are done. We should end up with something that looks like that. Whoever your advisor is, you gotta tell them, you can't do this to you. They're,
I don't even want to go.
then you are staying here.
Well, no,
I-
the thing is
I
they're
ordered
not
you
gonna
to
let me
as a
register.
professor of mathematics.
They're not gonna let me register for next semester if I don't go.
Okay. That's
And
bullshit.
that is a problem.
I would say that's bullshit though. Not you. You can relay that to whoever that is.
I love Dr. Narcissi.
Oh, is this? Oh, she's not gonna. I love her. Is this Dr. Narcissi? Tell her. I'm gonna. Hold on. I'm gonna tell her you're gonna be late.
Really? You would do that? Thank you.
You won't. I can just text her.
Just say, hey, your kid's in my class.
Abby is going to be a little late. And make sure that this is all going good. And I'll put a little smiley face and a little heart.
She'll really enjoy that.
No, we love each other. Yeah, she's a good friend.
She's great.
She
It's
is.
just that I don't really want to leave class right now.
That's fair enough. You're good now. You're done.
Thank you. I appreciate that.
Handled. I have very little power in this world, so anytime I can use any bit of my incredible abilities as a math professor to do something. Does this look okay? Are we good with this? Yeah? Yes, sir.
So when you divide 17 by 2, you get 8.
Yes.
Why wouldn't that be 8.5? Or you just,
So we're only doing whole number. It is 8.5, but this is only keeping track of the whole thing, the whole amount that goes in, and then if there's a fractional amount, we put that remainder out here. So the fact that 17 over 2 is 8.5, absolutely, Paul, that just says there's a remainder.
okay.
8 full times, and then half of a 2 goes in. All right, cool. Let's do the, oh my God, I can't believe it, this is so great. Oh shit, you guys, I'm so excited because then, not only, this is going so well. First off, thank you, this is going well because this is near and dear to my heart. But once you understand this, I'm gonna show you probably one of the greatest things I know in mathematics next week. Literally, one of the most fucking amazing things I can show any human being. You will be able to see it, you will be able to do it. And your mileage may vary on how excited you are about
Sometimes when I tell my parents what I've learned in this class, they're like, alright.
it. Did you show them your flexa?
No, but when I went home one time, I was doing my homework and stuff for your class, and they were like, this is a math class? And I was like, yeah. And they're like, what the fuck are you doing? I was like, I don't know, but it's fun.
Good. And that was all I was ever shooting for. Okay, so anyway, all right. So we now know how to go between whole numbers that are decimal and binary. We can go back and forth on those. But the fractional part is where things get a little interesting and kind of exciting as well. So here's how to convert decimal fractions to binary fractions. And this literally, this first thing, a lot of people maybe have seen that. Nobody knows this. Nobody knows this, except maybe some computer science nerds. Okay, so I don't know how to write this out, so we're going to do a bunch of examples. I'm going to show you how this works, because I don't have a nice clear step-by-step thing. So let me just show you by example. Convert 0.125 base 10 to base 2 binary. So you start with your decimal, write it out. So here's the original. So this is the decimal version, and then over here I'm going to write binary. And I'm going to start off 0 point, because it's going to be a fractional thing, so I start off like that. Instead of dividing by 2, we multiply by 2. So we're going to multiply by 2. And what we're going to record is the first number to the left of the decimal point. So check this out. So that goes to 0.250. I record that number over here. Again, I do it. So times 2 again, and I get 0.50. I record that number. Next. Times 2 again, and I get good old 1.0. I record that number, and I am done, because after this, so first off, you can check to make sure that that's 0.125, because this is an eighth right here. So that's the eighths place, this is the quarters place, and this is the halves place. So look, that's just an eighth in base 10, that's 0.125. I was thinking, what's an eighth? Oh, it's 0.125, let's convert that to binary. When you get a 1 out in front, you record it, and then eliminate it, replace it with a 0, and keep this process going. So watch how, let me say this all again. Keep multiplying by 2. Record the number to the left of the decimal point. If it's a 1, record that, make it a 0, keep going. So this one is done. There's no number left here, so this process is ended. Let's do something a little more interesting. Let's do a third. So let's convert 1/3 base 10 to binary. Step 1 is I got to get the decimal representation of a third. So I get out my calculator on this, and we know that 1/3 is, does anybody know this off the top of their head?
0.6667. Oh wait, 333.
Yeah, the other one. Yeah. That's it. It keeps on cruising, right? We've all seen that. This is one of the first infinite decimal expansions you probably learned. And we can write this with a shorthand like this. You probably have learned that notation where you just put a bar over the repeating part. And then people understand what you mean. So let's convert this number to base 2. So here's the first one. I'm going to multiply by 2. So now, Bella, we're going to have 0.66666. So times 2. And I've got 0. Yeah, that one's not too bad. And I record that 0. So here's my binary version. I start with a 0 point, and now I'm recording that 0 over here. What's that times 2? Might need a calculator maybe, but we could do it in our heads. 1.3. Oh, look at you, yeah, 1.3333333. Because this is actually 2/3. And what's 2 times 2/3? It's 4/3. So it's 1 1/3. So this is going to be times 2, gets me 1.333. dot, 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 dot. So I record the 1, strip the 1 of its 1 hood and change this into 0.333. So drop the 1. And now look, I'm actually back to where I started, right? This is literally where we started with 1/3, 0.333. So let's just convince ourselves of this again. I've already recorded the 1, so now I multiply by 2. This doesn't get recorded. That's the result of this. So times 2 again gets me 0.666. And I record that here. Do you see that I might be in an infinite loop here?
Yeah.
Yeah. And so I multiply by 2 again, and I
It's
get
just
1
gonna do
point.
the exact same thing.
Yes, it is. So now I record the 1, strip the 1, and I'm back to where I started.
You're just gonna keep repeating it though until.
Beautiful observation. I'm never going to end this process. In fact, this process is just going to keep going forever. Yeah? And this is the binary expansion of a third. Pretty crazy. And I want to show you something even crazier about this. It's somewhat mind-blowing. Like, this is like Calc 2 level shit that we're talking about right now. Might as well be in Calc 2 for all intents and purposes. So here's our base 2. We could write this in the repeating format, so we could say, oh, it's 0.01 and that just repeats, right? Get that information across, use that same idea. But what does this actually look like here? So let's see. Let's look at the places. This is the halves, quarters, eighths, 16ths, 32nds, 64ths, 128ths, 1/256, 512, 1024, and so on and so on. So what this means is that 1/3 could also be written as a quarter, 1/4, plus a 16th, plus a 64th, plus a 256th, plus 1024, on down. If I kept on adding these numbers up, eventually, at the end of time, they would add up to a third. Now that sounds really weird. It sounds really strange, but it's not that crazy. So let's talk philosophy. Zeno, we've heard of Xenos Paradox, maybe? So Zeno, the Greek philosopher, did a lot of studies of motion and philosophical explorations of motion. And one of Zeno's experiments was this. He thought he had proved that nothing could move because of this. So for me to get from here to that wall, I have to travel half the distance. Now to travel from here to there, I still have to travel half the remaining distance. And then I always still have to travel half of what's left. So Zeno reasoned, you're never there. You never arrive at anything because you're always just traveling half of what's left to be traveled. Now we know that's bullshit.
I'm telling you.
That's it. Yes, yeah. Yeah.
Thank
Good, I
God
hope
you were
that's
out
it.
of the view of the
I
camera.
hope that's on video. That's good. Zeno was chilling with the oracle, right? But maybe. But that's a really crazy way to think of this, and this is going to be part of the amazing thing I tell you next week. But you don't need to understand that. All you need to do is be able to convert. Can you do me a favor? Can you convert 1/10 in base 10? No, let's do 5th, easier. Let's do a 5th. Convert a 5th into base 2. Your first step is realize that 1/5 is 0.2. Get me the binary expansion. see that we're starting to repeat again? Isn't that cool? So we end up, we go through all this, and now we're back at point 2. That's where we began, so this isn't going to change. That just repeats forever. That rhythm of remainders is going to be 0, 0, 1, 1, 0, 0, 1, 1, or the things that we're grabbing. That's it. And so when you enter on a computer, you go to the terminal, and you type 0.2 and you hit enter. The computer has no idea what 0.2 is. What it stores in memory cells, because it only understands off and on, is something like this. And then here's the problem. It's got to stop somewhere, right? It has to eventually. Computers are finite beasts. If you have like a 16-bit computer, that's pretty old school, but that means you only have 16 of these to record things. You only have 16 little spots in here. I think most computers these days are 64-bit, so you've got 64 of these places you could use, but eventually it's got to call it. And what do? Do you round up? Do you just cut it off? That's an issue that somebody has to think about, and computer engineers have to think about. And it's also the reason why on a computer, if you add these two numbers, you don't get the same thing as if you add these two numbers in this order. This is real. If we had a Python interpreter over there, I could show you that 0.1 plus 0.2 gets you a different result on the computer than 0.2 plus 0.1. They're both pretty damn close to 0.3, which is good shit. But one of these has a little bit of a tail stuck on it because the computer can't understand perfect numbers. It has to approximate everything. And because of that, we've got to be very careful what we do. So friends, that was a good day. That was a very good day. So now on this sheet, let's see, what can you do? Oh, how would you convert? One last check. No. One last thing. How could I convert to base 7 or base 6 or something? So let's just do this really quick. So then you can knock out a bunch of these if you want. Convert, let's just say 100 base 10 to base 7. How do I do that? I start dividing by 7 and recording the remainders. So 100 divide by 7. Oh God, what's that going to be? 14? That get 14 times 7 is 98, and so you got a remainder of 2. Divide that by 7. Kind of beautiful, right? So I'm dividing by 7 right now. Goes in 2 times remainder of 0. 7 doesn't go into that, so I'm done. 202 base 7 is 100 base 5. Check how slick that is. I'm just dividing by the base and converting. And you can check this out, because this is the 1's place, this is the 7's place, and this is the, this is the 7 squared's place. So that means it's 2 times 49, plus no 7's, plus 2 1's, 98 plus 2. Oh, hell yeah, that is 100. So now you can do, let's see, what can you knock out? And please, write up all the details for this. Don't do your work on this sheet, please. Do it on separate sheets and put your final answers on here so that it's easy for me to find them. You can do problem 1, 3, probably 4. Yeah, you can do 4. You can do 5. You can do anything except the hexadecimal stuff, I think. So you should be ready to roll on any of this except hex. And we'll talk about that on Monday. And we'll learn how to feed. So hexadecimal numbers include A through F. So when I was and this, you don't have to write this down, but when I was a computer programmer at IBM and you're just looking at memory dumps, people would fill the memory with these characters. dead beef. I just remember looking at memory dumps, seeing dead beef, dead beef, dead beef, just to fill up the space with something that was obviously kind of weird and funny. All right, you guys seem like you're really cracking up about that, so try to drive safely.
Thank you for texting that.
Thank you. And if there's any problems, please have her contact me and blame me, okay?
Okay.
I'm serious.
Be a problem.
Well, I shouldn't be, but see you on Monday. Have a good weekend.
I gotta bring the tape back to so